Hello everyone, welcome to my session. My name is Srikanth Dandolu and I am a lead software engineer in a financial firm. Before we dive into the core architecture today, I want to give you a brief idea of the lens I look through when designing these systems. I hold a master's degree from the State University of New York and I have spent over 14 years navigating the trenches of complex database environments. Over the course of my career, I have worked heavily with massive enterprise data products, spanning everything from traditional Oracle databases to modern cloud infrastructures. Through years of architecting scalable solutions and deploying enterprise-grade capabilities, I have seen firsthand where legacy systems bottleneck. When you are operating at an enterprise scale, traditional batch processing simply cannot keep up with the demands of modern business. That is what brings us here today. We are going to dive deep into the architecture and the real world impact of AI powered analytics. We will look at how real time processing is fundamentally changing modern data platforms, moving us from reactive reporting to proactive modern business. We are we are in the middle of major shift in how we handle data. This isn't just about incremental upgrades. By integrating AI directly into the analytics pipeline, we are seeing processing times drop from hours to milliseconds. These kind of speeds gives us faster insights, much higher accuracy in detecting anomalies, and ultimately massive cost savings at the enterprise scale. What does this look like in practice? The most immediate impact is on the bottom line and the operational efficiency. By caching data quality issues earlier and automating the remediation process, we dramatically reduce manual overhead. This means decision-making cycle gets faster across every single level of the business. Of course, speed means nothing if the system isn't reliable. These model architectures are built for high system uptime and continuous availability. Even with high volume transactional processing, we can sustain throughput while keeping false positive alerts rates incredibly low. Now, let's look under the hood. Our technical architecture is built on a purpose-built four-layer foundation. In the past, managing heavy monolithic databases meant that ingestion, processing, and analytics were often fighting for the same compute resources. These architecture fundamentally solves that by decoupling the layers. So we have like four layers. Layer 1 handles high capacity data ingestion. We completely separating the analytical read load from the primary transactional databases so we don't impact the source system performance. Layer 2 is the processing engine for real-time streaming. This is where we shift from batch window dependencies to continuous stateful processing. Layer 3 is where the AI and machine learning models live for predictive capabilities, securely isolated but highly accessible. And Layer 4 provides seamless integration to get these insights out to the rest of the ecosystems via an optimized APIs. The heart of this platform is real-time data streaming. Batch processing simply can't keep up with the demands of modern AI models. If you have spent time managing large-scale enterprises databases, you know that traditional pain of overnight ETL jobs, bad jobs. Say if a job fails at 2 a.m., the business doesn't have the data at 8 a.m. We have moved away from that entirely. Now we need a continuous, synchronized flow of data to feed the intelligence engine. By streaming data in real time, the AI models are reacting to what is happening right now, not what happened yesterday, which drastically reduces our main mean time to detection for critical anomalies. Three key components make this pipeline work. First, change data capture. Change data capture keeps everything synchronized in real time. Second, our feature stores centralizes, centralizes how we manage and serve features for machine learning workloads. The third, optimized streaming. This ensures high throughput without burning through compute resources. In the processing layer, which is really where the heavy lifting happens, we rely on tools like Apache Flink for enterprise scale stream processing and sub-milliseconds in memory caching. To ground this in reality, let's talk about the actual pipeline. Our real-time transformation pipelines pull changes, data captures from massive relational databases like Oracle or Aurora PostgreSQL. By utilizing CDC, we are reading directly from the database transactional logs. This is critical because it allows us to extract high volume data changes continuously without putting expensive query loads on the primary database engine. Once that data is captured, we trigger event driven processing via AWS Lambda. Relying on the serverless compute like Lambda is highly intentional. It allows us to scale our processing power instantly per event without managing underlying instances, driving driving down ideal compute cost. From there, the data integrates seamlessly into warehouses like Snowflake or Data Lake. On the machine learning side, we use TensorFlow servings for production-grade deployments, supporting concrete model versions and automated drift detections. Data is only useful if it's accessible. We use a multi-protocol approach so downstream consumers can integrate without friction. We use REST for general queries, gRPC for low latency internal service communications, WebSockets for live dashboard updates, and async processing for deferred workloads. Building this wasn't without challenges. We had to tackle latency, optimization, and scale head on. When you are combining legacy database systems with cutting edge AI, the bottleneck is almost always I/O wait times or connection pooling limits. So we use multi-level caching to crush down latency so the AI doesn't have to constantly query the disk. On the AI side, we use model quantization, which essentially compresses the neural network to keep machine learning interface incredibly fast even under the heavy transactional loads. We finally implement elastic autoscaling. So whether the system is handling normal traffic or a massive end of the month spike, the platform grows seamlessly alongside demand. So despite all these automations, the goal isn't to replace the analyst. It is to supercharge them. By using intelligent task allocation, the system routes complex, nuanced problems to human experts while handling the routine data lifting itself. So this reduces cognitive workload and actually increase the analyst's confidence in the system. Generative AI has been a game changer here. We use it for document intelligence to extract patterns for better than traditional OCR. It automates routine queries so users can just ask questions in natural language, and it generates tailored multi-language reports for different stakeholders. Security has to be baked in, not bolted on. So our framework uses multi-layered defense mechanism to block adversarial inputs. We do real-time input validation to prevent data extraction attempts backed by automated incident response to catch threats immediately. So AI cannot be a black box. Therefore, we use explainable AI, which is XAI. So every decision is transparent and auditable. We also actively mitigate historical bias in our training data to ensure equitable outcomes, and we utilize privacy preserving federated learning so we can train models safely. The numbers speak for themselves. So therefore we are seeing like 99.97% uptime, and the throughput capacity is handling over 100 million events per second. And the business impact, a 95% efficiency gain and documented cost savings of up to $75 million. So what's next? We are looking towards deeper integration of transformer based NLP models and more privacy preserving auto machine learnings and fully serverless AI infrastructures that scales on demand to support truly autonomous analytics. As we bring everything together, I want to leave you with this organization that embrace AI powered analytics are positioning themselves for a sustained competitive advantage. Real-time insights are no longer just an aspirational goals. They are new baselines for the strategic leaderships. To summarize the architecture and impact we have discussed today, first, the transformational is already achieved. We are talking about document savings of up to $75 million, dollars, a 95% jump in operational efficiency, and maintaining that critical 99.97% system uptime. Third, the real power lies in human and the AI synergy. As we discussed, these collaborative architectures consistently outperforms human or AI working in isolation. We are supercharging our engineers and analytics teams and not replacing them. Fourth, the time to innovate is now. The window for serious competitive differentiation is open, and the time to act on these streaming accessories today. So that covers the core of our presentation. To wrap up our session today, I want to address two critical questions that come up frequently when we talk about implementing these systems at an enterprise scale. The first question: What are the key architectural components required to enable real-time AI-powered analytics in modern data platforms? To make this work in real time, you can't rely on legacy batch processing setups. Drawing on my background in cloud ecosystems like AWS and relational databases, I always emphasize that you need to purpose build four-layer foundation. First, the ingestion layer, high capacity event streaming and CDC to pull incremental changes instantly. Second, the processing engine, where technologies like Apache Flink handle stateful stream processing and sub-millisecond caching. Third, the AI ML layer, a centralized feature store for consistent computation paired with production grade and model deployment. Fourth, the integration layer, a multi-protocol approach using REST, gRPC, and WebSockets to ensure insights makes it to downstream consumers. Now, moving to our second question, how can organization balance performance, scalability, and cost while implementing streaming and AI-driven analytic systems? This is a million-dollar question. The key to balancing these three pillars is elasticity, and intelligent optimization. First, for performance, we tackle latency through multi-level caching and model optimization techniques like quantization. And for scalability, you have to decouple compute from storage. By leveraging elastic auto-scaling infrastructure and leaning heavily into serverless technologies, the platforms can seamlessly grow with demand. Third, the cost, which is important for any organization. Because we use that elastic serverless approach, you aren't paying for idle bare metal servers. You only provision the compute you actually need. When you combine that with intelligent task allocation, routine simpler queries to automated engines, and reserving heavy compute for complex machine learning tasks, with this you achieve massive cost savings while maintaining the 99.9% uptime. So by getting this architecture right, organizations don't just save money, they fundamentally change how fast they can react to their data. With this, I would like to conclude our deep dive for today. Thank you so much for your time, and I truly appreciate you joining me for this session. Thank you.